Hello everyone, this is Korenaga, and I'd like to thank the Asia Seismology section for this opportunity to talk about our recent paper on a new reference model for the evolution of ocean lithosphere, which is a collaboration with Jun Korenaga at Yale University and Hitoshi Kawakatsu and Makoto Yamano at the University of Tokyo. In this lightning talk, I would like to focus on some historical background behind this new model. The first things I want to emphasize is that different things can happen during the evolution of normal submersion mantle. That is, even if we don't think about external perturbations such as mantle plumes. This illustration summarizes those processes intrinsic to the normal submersion mantle, such as thermal cracks, pressure melting, small-scale convection, radiogenic heating, and secure cooling. Some of these processes cannot be very important when we try to explain SuperTopography. As we know, if we plot seafloor depth as a function of square root of seafloor h, it follows a nice linear trend with a slope of about 300 meters per square root of million years, at least for the young part of seafloor. 5 years ago, we found that it was actually not easy to explain this observed subsidence rate because if we do modeling with the most complete mineral physics treatment, the subsidence rate should be as high as 500. This is created a problem, but we also found that we could reduce this prediction by incorporating the effect of thermal cracking, radiogenic heating, and secure cooling as shown here. This figure shows the same things in a more direct way. This black line is the subsidence prediction we got by putting in everything we know about mineral physics, and that's too steep. And by adding the effect of thermal cracking or incomplete viscous relaxation, we get this blue curve. By adding radiogenic heating, we get this orange curve. And by further adding secure cooling, we get this red curve. What we did in our most recent paper is to extend this model to all the seafloor. And to our great surprise, this model, which is essentially a half-space cooling model, can naturally explain seafloor flattening, as you can see. The following two issues are worth highlighting. One is Earth is cooling, as indicated by this cooling history of the upper mantle over the last 4 billion years. And the other is the long wavelength of topography is sensitive to deep mantle density anomalies, as shown by these topographic kernels. We know both of them for many years, but for some reason, they are absent from previous models on the evolution of the subsidence suboceanic mantle. In our paper, we of course discuss how the new reference model can explain relevant observations such as seafloor bathymetry, surface heat flow, and the seismic tomography of ocean's upper mantle, and also a few other important issues such as small-scale convection. So I hope you will enjoy reading it. Thank you very much for your attention.